All right. Welcome back, everybody, to episode slash day slash step 10 to becoming an AI engineer. Um, Yesterday, we had started going down the road of this video, understanding how to create a neural network, and specifically a plain neural network and not a one with convolution layers involved. But we're going over everything, and we really got a great understanding of weights. Uh, the weight, uh, taking the definition at face value, is it scales the impact of the input, right? But in order to digest this as well as we do now, in my opinion, understanding what an input is key. So, input is going to be any pattern recognized within any data given to the algorithm to be trained. So, if we're trying to determine between apples and oranges, perhaps the shape input might have a low weight because they are very similar, but the color input will have a higher weight as uh, it's a stronger differentiator between the two. Now, where that decision boundary lies will be in a location around where the shape and color are so similar, perhaps that, and this is within the weight, right? So the weight of, let's say, the shapes are somewhat different while the colors are somewhat the same. This would give you a decision boundary of zero. I mean, this may and wind up being a a prediction score between both of zero. So that's where you would draw your boundary for your decision making line. Sorry, your decision boundary, and how certain things like safe and poisonous can be
Weight
calculated.
of its
So
connection,
let's keep going down this path. Uh, like we said, let's see what we can learn for the next hour.
plus the second input multiplied by the weight of its connection. And it'll be the same story for the. I've quickly written up some code to perform this calculation, which you can see in the classify function over here. Then to visualize what's going on, there's this visualize function, which gets run for every pixel in the graph display, and it asks the network to predict whether a fruit at that point would be considered safe or poisonous, and then colors the
I
graph
don't know
accordingly.
why everything
So
is being so
let's see what
slow
this
right
does.
now. Let's try to close some things. See if that might help. There we
At the moment, it's very paranoid and seems to think everything is poisonous. But up in the corner here, we have our network weights. So I'll play around with these a bit to see if I can get that decision boundary how we want it.
So, as you can kind of see, if I get it to pause, as you can see, as he fluctuates the weights, the decision boundaries change. Now, we already have these labeled pieces of data that we are aware of, right? We have this data point here where we're saying it is the, I think it was the spike length is the y-axis. So let's say the spike length is right below average, uh, right below the median, right? Whereas the spot size, which I believe was the x-axis, is relatively small. So because the spike length hasn't grown into the danger territory and the spot size is relatively small, this is considered, well, first it's already considered safe. But now we have the data that safe is considered safe when the spot size is relatively small and the spike length is lower than the median, right? So we want the AI to be able to understand this decision right here and understand how to start this decision boundary. So by doing that, if we raise the weight of the impact of, let's say, the spot size, then that means somehow, some way, whatever the calculation is, whatever the situation may be, as it goes through all these and starts solving all of these, it'll automatically fix the weight so that here we could say, okay, well, the spike length weight should really be somewhat low, right? Well, it should be average, right? I feel like both should be pretty average because they're stop and start from poisonous to uh poisonous to safe relatively within the same. No, I guess inside the same area would be more here, and it'll come across like that. Or maybe would that be? I don't know. Honestly, I don't know how the statistics would work. Um, but I will say,
Unfortunately, no matter what I do, I can only get the boundary to
I will say at this point we're at a point where I am definitely understanding the concepts, but I have to still refine it more in order to be able to explain it back.
essentially rotate around the origin of the graph here, when what we need now is to be able to shift it vertically. So let's go back to the code and make a tiny upgrade to our network by adding in two new values called bias1 and bias2, and these will simply be added on to our weighted inputs over here, allowing us to move those values up or down.
So now we understand weights. How I want to understand the bias in the context of how does the AI learn to add a bias? Because what's being said here is output one versus output two. Why are we biasing in this situation more towards safe versus poisonous and vice versa? Why would we raise the bias higher for poisonous versus safe? Let's try to understand that. Bias starts at a random value of 0 after a forward pass and loss calculation. Backprop computes. It does a computation. The optimizer, which we looked at before, performs. There's no special rule for bias. It's just another parameter. Line must pass through. Boundary can shift, not just rotate. So, okay. So it's just added. I mean, we want a linear equation, right? And a linear equation on 0 doesn't really help us much, so we need that bias. That's understandable. It's the same
Okay,
way
let's give it
weights
another
work. I'm
shot.
not sitting here asking, what's the formula function that's being ran for weights to be altered. That's not necessarily important,
So I'll fiddle with the weights again to try
in my
get the
belief.
angle of the boundary correct,
So
and
as he is moving these weights, this first weight, he's moving the boundary. And to me, this first weight, let's see here. So you have four weights. And we're saying within the x-axis and the y-axis of whatever the input is, whatever that data point is, you're going to have a poisonous, you're going to have a safe or poisonous output. So by working with the first two weights, you are saying on this data point, um, working with the first two weights, you're essentially saying with this input of each, I see, I see. We're lucky because it's two. I understand. The whole graph situation is what I'm understanding right now is the only reason it works is because there's two inputs, right? If there was 3, 4, 5, 60 inputs, this formula in itself would be a lot longer, but it would still handle that calculation, right? If it was the spike length, if it was the spot size, if it was the color, if it was uh, the the shape, if it was just the size in general, right? We have six different inputs. We still need to be able to essentially plot that. Not as we don't need to be able to plot that. The reason we can plot this is because it only has two inputs. So let's take a step away from the graphing aspect of it because it is very constrained just to this. But if we understand the fact that these weights are going to be applied automatically to every single input based off of laws, based off of the gradient descent, returning us whatever calculations it's returning. It'll be updated so that each input then maintains a correct weight to it. In order for each output, which we define, right? In my opinion, we define the outputs of whether it's receiver or cornerback, whether it's poisonous or safe. The inputs, though, are going to be automatic. So let's verify that we're understanding that correctly. Uh, due to it being data set, right, which is going to be the data plus the label for inputs that all get automatically weighted. Also, the bias of update. This is my understanding. Yes, that is accurate, but now refined with precisions. Okay. You can only graph a decision boundary because the model has two inputs, allowing the boundary to be visualized as a 2D line. Okay. Okay. I'm tracking. It's still a mathematical surface. Yes, it exists inside of those hundreds of dimensions. So, I mean, you can think of it maybe as a cube even for the next if it has three plots to where you have, let's see here. If we're saying that we have a cube, or, whoops, not the best cube drawer, I guess, something like that. So we have a cube, and if you think of this as the x-axis and this is the y-axis, then inside the cube, right, you also have your depth. So inside of here, this can be so you have, let's say, something um, with, let's change colors actually. So you have something with relatively small spot size with relatively small spike size, but it has, this is us going inside the cube all the way to the back end, but it has, let's say it's, let's say this is just the size of the cube, right? So all the way deep, all the way back as far as you can go depth wise. This is touching the back facing wall, right? Over here. We'll say we're over here, right? Over here on this back facing wall, you have this touching it, which is saying the size of the fruit itself. Because it's here, all the way at the back, although these are relatively small, now we have this third parameter, which then classifies it as poisonous because the weight of this third parameter might be greater than the weights of these two combined, right? So even though these would normally wind up being non-poisonous, now that we're using another parameter, another variable, it now becomes poisonous. So yeah, you can't visually represent something with hundreds because we have no idea how to represent that on a computer. Uh, the weight associated with it is learned by gradient descent. Yes, bias is just another parameter updated the exact way. Wonderful. So when a model has 150 input features, the decision boundary is still created by the same equation, but it exists inside a, I want to say, in one-dimensional hyperplane. Dimensional hyperplane. I see. It's not saying in one, it's saying 149 dimensional hyperplane, starting at 0, going to 149. Reshape space so a hyperplane becomes sufficient. Distinction separates beginners from people who understand deep architecture. A deep neural network does not learn to draw the curved boundaries. It learns to transform space so that uh, uh, so a hyperplane becomes sufficient. So that a hyperplane becomes sufficient. Neural networks aren't covering boundary, they're covering the space. Essentially gravity, huh? Um, I see. It is essentially like gravity. That's insane now that you think about it. If you think about like the space-time continuum, gravity. If you think about it like this, the the boundary line might be, a line separating here, and then everything on that x-axis, everything on that y-axis, and then everything inside this little chunk right here might be receivers. Then you have depths to it. But again, we're talking 140, however many features, however many variables. So, okay. So, anyways, we're constraining to just two inputs and we're applying an arbitrary weight to those two inputs. That's what he's doing by sliding it around. And then if the output of safe or poisonous is larger, if the output of safe is larger than poisonous, you are outputting safe essentially, which in turn, I see. So you're predicting class, which is running this based off of the input output. Okay.
Tiny upgrade to our network by adding in two new values called bias 1 and bias 2, and these will simply be added on to our weighted inputs over here, allowing us to move those values up or down. Okay, let's give it another shot. So I'll fiddle with the weights again to try get the angle of the boundary correct, and then I'll move on to the biases. It's a bit finicky to control, but with some patient tweaking, we should eventually be able to hand train our little network to correctly.
So think about this, right? We're saying if we do it relative, this can be the weight of spikes connected to the output of safe. This is the weight of spot size connected to the output of safe. This is the connection of spike length connected to the output of poisonous, while this is the connection of spot size connected to the output of poisonous. So as he raises the weight of the importance essentially of spot size, it starts to match what the decision boundary should be. And then you add a bias to spike length, and it also helps correct. So now the AI manually knows, okay, if I bias strongly to spike length while raising the weight to spot size, I can match everything perfectly.
classify the fruit in our training sample here. This was a pretty straightforward task though, so let's imagine that when we collected this fruit data, it actually ended up looking something like this instead. This is trickier of course because we can no longer separate safe from poisonous with a straight line, so we'll need to make some more upgrades to our network. One way we could try to improve the network is simply by making it bigger. It doesn't make sense to change the number of inputs or outputs because those are determined by the problem we're trying to solve, but instead
Right. The inputs are, I mean, technically he can't change the input and still represent it in a 2D shape, so that's first. The output makes sense because he's trying to do rather poisonous or non-poisonous. That's all we care about. So those aren't going to matter. So what is he going to do in between now?
we can create a new layer that sits in between. These in-between layers are known as hidden layers for whatever reason, and they can have as many nodes as we like, and we could even have multiple hidden layers, but let's keep things simple for now. So as our input values get fed forward to the next
So now we're saying the inputs are being fed to the next layer, but it's no longer the output.
layer, they'll be multiplied by their weights, as we've seen before, and added up with a bias value, together creating a weighted input for that node.
But it's for, huh. So you have the input of spike length and spike length and spot size. You give those the multiplication of their weights and you add it to this with the bias, and then you do the same spikes length, spike spot size. But what is this? What is this compared comparatively to the output essentially?
And once that's been computed for all the nodes in the middle layer, those values can then be fed forward in the same way to form the weighted inputs of the next layer. Even for this extremely tiny network with only 12 weights and 5 biases, it would be quite tedious to write out all the calculations by hand like I did over here. So I'm going to throw all of this code out and start working on a more sensible solution.
Okay, so let's see.
So I've begun by making a layer script which stores the weight values for all the incoming connections, along with
So before we continue, I would like to figure out what is a weighted value input. No, 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 no. What is? Good Lord. What is a weighted value when you add hidden layers? For a neuron, every input is multiplied by a weight before being summed. Yes. Numeric result of multiplying each input by its learned weight and adding the bias. So use only the weighted sum. Hidden layer. The output of one layer becomes the input to the next. Those outputs are themselves weighed inputs for the next layer. So this is doing this is essentially the convolution layers. So okay. So the output of it becomes what? The input. Output of a hidden layer becomes the input for the next layer. It's not necessarily that it connects directly to the output. It will eventually, but the point is that it just simply becomes the input. So that being said, Let's try to walk this out. So you have, let's say, forward lean, and you have foot stagger. And I'm going to take, and these have three hidden layers, is what he's saying. And then I'm saying for each, I'm going to do this, do this, I'm going to do this, I'm going to do this, and then I'm going to do that, and then I'm going to do that. Right. So if this is this weight for this layer, I see. So this layer, this output is going to already associate a certain weight with this. We'll just say this is A, B, and then C. So for the forward lean connection to A, the weight might be 7. For the forward lean connection to B, the weight might be 4. For C, it might be 2. And then for the foot separation connection might be 6 on A, 1 on B, 2 on C. So from here, we'll do whatever calculation, right? But let's say it's as simple as 6 plus 2, so 8. And then the forward lean for B plus the foot separation gets you 5. And then for foot separation to C, you're doing 2 and 2, so you have 4. My assumption is that now from here, we have the number 8, number 5, number 4. The same way we would have had a number here of whatever number, right? X number, and Y for the forward lean and foot separation. That calculates to a new number, which then gets fed into the final. Wait, what is that? What happens after that?
With making a layer, start working on this extremely tiny net.
You say you have 3, and then all 3 go to, we'll say all 3 to safe equals something. And then you're also going to have all 3 to poisonous equals something. Um, and the reason these are going to equal different things is because the connection for A, this what you could consider your first convolution layer, is going to have a different weight than it would for poisonous. So if I raise the weight for safe here, what happens, right? Do I get it right or do I get it wrong? Now we're saying, okay, after the first convolution layer, we'll raise the weight for cornerback and lower the weight for DB, I mean, for receiver. And then this will give us said number here. And then this will give us said number here. And so it is considered safe because the forward lean, no, because things here gave us a number here, which then worked with this here to connect down to the final output uh, by giving us weighting outputs of all this in the layer. Now, I just don't know what is defining the layers. What exactly is defining the layers, or is that something that is going to be happening automatically? Y is essentially y equals mx plus b, the input vector from previous layer. So we're saying if we're here, we're saying that, hold on, weight matrix. the weight on the input. Yep, okay. B is the bias, activation function, and the output is Y, which becomes the next layer, next input for next layer, which is 854. If we're just talking about, yeah, so A is 8, B is 5, C is 4. The same way forward lean could be, it's 4. Okay, yeah. The same way forward lean is X and the foot separation is Y. This calculates to something to be A, B, C, which are just other numbers, which then gets passed the same way to the next one, which will have certain weights. Gotcha.
Network with only 12 weights and 5 biases, it would be quite tedious to write out all the calculations by hand like I did over here. So I'm going to throw all of this code out and start working on a more sensible solution. So I've begun by making a layer script which stores the weight values for all the incoming connections, along with bias values for each node in the layer. And these get set up over here.
It is not letting me click on the video at all the way that I want to, so let me try to. Yeah, it's a lot better. Go.
One way we could try to improve inputs and in tiny more sense of hand and values for all the.
So now we're making a change so that we're not writing all the code out by hand, and we're saying the integer of number of nodes in and the integer of number of nodes out. Now, to me, you shouldn't be able to define this number of nodes in. The only reason he is doing it is due to the fact that he wants to be able to plot it on the graph. Now, let's verify. Basically, we'll be able to specify number. I don't like saying right because I don't want to prompt it in a way that's you need to explicitly choose a number of nodes per layer. And densely, you choose a number of nodes per layer. You do not define the nodes, you define channels. Number of filters, each filter produces one feature map. So each filter produces one feature map. A feature to me is spike length, uh, fruit size, right? So you're saying each filter, each layer, then out of what it's trying to find, finds that. So if we're trying to specify the fact that there's going to be a layer, well, not specify, I don't define it. I define channels. And inside the channel, if there's a layer that looks at patterns and then the pattern somehow gets to foot size or foot separation, then in that scenario, it would make sense that you see you see that connection there. Hold on, that my brain completely blanked while saying that out loud. The layers will find the same way that he's specifying the inputs, the patterns. The layers themselves will find them in convolutional networks. In dense networks, which is what he's doing now, he's saying the number of, well, no, but this doesn't, you define out channels, kernel size, stride padding. Well, we already know that. We know the purpose of AI is not to say we're specifying spike length and spot. It needs to find its own way. So we already know this isn't the case.
The incoming connections,
So you get your weights, your
along with bias
biases.
values for each node in the layer. And these get.
And you have your constructor here where you're saying you have to pass in the number of nodes in and out. So cornerback receiver. And you're saying this variable that belongs to the constructor gets set to the variable that's
Get
passed
set up
through it.
over here based on the number of incoming
Same with
and
weights and
outgoing
biases, that will
nodes.
work for everything.
Just to clarify, in the code, I'm thinking of this layer, for example, as having 3 incoming nodes and 2 outgoing nodes.
Makes sense.
Then this layer would have 2 incoming nodes, and 3 outgoing nodes. And finally, this layer really just represents the values given to our network. It doesn't
Three
do
outgoing,
anything,
though.
so it's not going to be an actual layer in the code.
Gotcha.
Alright, back to the layer script. All that's left to look at in here is this calculate output function.
So public double calculate output. So we have a function which ingests a double of an array of inputs, right? So the output of the layer. So you're calculating all the inputs that came in, and then you are saying weighted inputs equals new double num nodes dot out, num nodes out, which is set up here at the level, at the high upper layer. Since we're only using one hidden layer, to me this works perfectly fine because we know what the num nodes out is going to be. We know it's going to be 2.
Which takes in some input values and computes the weighted inputs simply by looping over each outgoing node.
So for int node out equals 0, right? Because we're going to loop and we don't want to go over, while the node out here is less than number nodes out. So while 2, so you have 0, so that's the first pass. Then you have 1, that's the second pass. And as long as 1 is less than 2, which it is, do the function. But once it's 2 nodes, then it's not going to do the function because node out is going to be equal to node nodes out. So then you say double the weighted input, which we are getting from where are we getting weighted input from? Equals biases node out. The bias on I see. So you have different. Okay, sorry. So you have biases, which is going to be an array, and inside of this bias array, you're gonna have 0, which is gonna be, let's say, safe, and then you have 1, which is poisonous inside of this bias array. Right? B, you have the index of 0 and the index of 1 inside of this array. And say we have a bias to safe of 10, and then a bias to poisonous of 5. So then we say for int of node n, which is starting at 0, while we go through 0, 1, let's say there's 3 nodes n, 10, 5, 7. Now let's say these are nodes n. You have 10, 5, 7, and for int node n equals 0, so for 10, weighted input is plus equal input of node n, which is saying 0, and inputs exist. Where does inputs exist? Here. Wait. I'm missing something? Because we're saying inputs plus equal inputs node n times weights node n, comma, node out. Where is, so the variable weighted input plus equals, essentially adding to the running input. Um, and then this is setting it so that when it loops again, it keeps it'll be able to keep the count going basically. So and this weighted inputs array, you're getting the array index and you're setting the weighted input into there. Um, so for integer node and for zero, so it's a for loop starting at zero, going to however much to run through all of the nodes of n. So if we look at, if we say here, here, one, two, three, one, two, like he had it. So let's say we're starting here and we say, uh, we create a layer and num nodes n is 2, num nodes out is 3, and then the weight to biases is just numbers. So then you say this new double
setting the
weighted inputs is equal to the new double num nodes out, which we're saying is going to be 3 for this layer. So right now we're working layer 1. Right. 1, and we're saying the output are 3, inputs is 2. Actually, we said this isn't going to be a layer. So let's hop over here to layer 2. That's what he said. We'll try it first, but I also am aware of him saying that the input nodes are 3. Okay. So let's try layer 1 first. You have a double array of weighted inputs equals the a new double of number of nodes out. All right. Hold on. Give me. I'm gonna be right back. All right, where were we? Let's see here. So the biases. So the weighted input. Am I not understanding the syntax? It might be as simple as that. We gave it a good kind of dive. Let's see if we can break it down a little bit. Uh, shoot. What's the shortcut off the top of my head? Shortcut to open. Control Shift T. Wonderful. Oh, that's unfortunate. I'll bring the chat up for next video. Well then, ain't that taking its sweet time? All right. While that does the while that does okay. While that does that, let's do it on our own too. So we're from my understanding, this is you're calling the double type and you're creating that variable of weighted inputs and it's equal to a new double and we're passing the num nodes out as the or you creating a new array or yeah, a new array. I see what that is. I think this is creating a new array for called weighted inputs and the amount I want to say either the amount of indexes inside of the num nodes out. No, because this is just a number. So you're creating a new double three or two in our case. Right? Yeah. So weighted inputs, double weighted inputs equals new double. I don't know. One fully connected layer of a neural network from the previous layer. Yep. So makes sense. Makes sense. Weights as a num in times none out matrix. Weights equals new double. Boom, boom. It's a matrix. And then biases equals that. Where does calculate output return? So here we are. Output weighted inputs. So inputs is a vector of length num nodes in. Output weighted inputs, right, is a vector of length num nodes out. So to me, a vector is saying the amount of weighted inputs. Am I crazy or what? Start weighted input at the neuron's base bias. So that's going up and down on the graph. It will then add contributions from every part, every input node, inner loop. Is that what it's doing? So you're starting on, okay. So you're starting on whatever y-axis, and then you loop through, and then you equals input of n, which is 0 plus the weights of the matrix of node n and node, or create another, for the fixed node out, this loop, right? 0 iterates all over all inputs node n for each. So iterates and does the calculation on all the connections from node n, takes the value of input node n being 0, right? So your inputs are your list. I see. Okay. So your inputs are your list. So you have, let's say, three inputs here. So let's verify this real quick. Um, is creating an array. Is the type array of double. Declares a variable named biases, whose type is array of doubles. No array is created yet. It's just saying what kind of thing biases will hold. Perfect. So bias equals new double, num nodes out, creates the actual array of memory with num nodes elements with each as a double initialized. Okay, perfect. That's what we needed. So, like, let's say here, we're creating biases, which is an array of doubles all the way up to num node out, which is 2. So makes sense now because you wouldn't have more than two biases. You would have number of elements, you have two biases because you have outputs of safe or poisonous. Weights, you have a double of your ins and outs. So you have your 3 here and then your 2 out. From there, let's actually just look back at the picture now that we're tracking what's going on. All right, let's go back to the video. So you're saying you create a new array of double type with the amount of elements of numbers of nodes out. Then you come down here to this function of calculate outputs, and you're also going to have an array of inputs with double, and then you're saying double. I see. You could use this anywhere because it's already defined up here. Instead of having to, I guess you don't have to. Is that a C sharp thing or in general that you don't have to then say inputs equals input, right? You could just specify directly from the parameter. I don't know if that's a C plus a C sharp thing. Actually, let's just check real quick. Is- So now that we understand that, we're saying we're creating an array of weighted inputs is equal. So we created an array of weighted inputs and we are setting it to the size of the num nodes out, which is 2, right? So then you say for int node out, which is 0, and then while that node out is less than 2, so plus 1. So then you say we create the weighted inputs equals biases, which are up here, starting at 0. Um, and biases is array 0. Where this is coming from, I don't really know, right? Double biases equals num nodes out, which is 2. So I don't know if you're creating, I'm going to say this is 0, right? For int, because this is probably getting set by him sliding the slider. That's what it is. So we're saying the bias for node out of bias of 0 is going to give us double weighted input. No, that doesn't make sense. Actually, yes, it does because it's just one. This isn't referencing the array. This is just a new variable. So you're saying this new variable, working with 0, we start the weighted input by adding, essentially starting with the bias, right? Because we're y of x, y equals mx plus b. We're saying b is starting it off, so the plus b is already there. And then you're saying for int node equals 0, so the first incoming node, which is our a, right? And I say a in the sense of here. This is a, this is b, this is c. So we're saying on A, let's actually just keep drawing this out, right? Let's do this. Let's do this. Hopefully you guys could see perfectly fine. Maybe. Let's see. Okay. So for integer, node 0, 0, 0, double of this weighted input equals biases of node out. So let's say there's a bias of 2 here on A. So we're saying for A, double weighted input right now is 2. And then we're saying plus equals input of node n, which is already had a calculation done on into it. So this a node already has a calculation done, and let's say this a came out to be, right, after I did this, of, let's say 3, 4, it gives us 7. So a itself is 7. So 2 plus equal 7, because that's node 0. That's node n0 for this second convolution layer, plus the weights of the matrix of node n, which is 0, and then node out, or times the weights of node in, node out, which node n is 0, and then node out is up here 0. So the weights of the weights of 0, 0, of weights 0, 0 equals new double, dun, dun. Oh, which also, wait, yeah, this is also being then set on that slider. So 0, 0, and then so let's say the slider is saying for node n 0. Hold on. Node n, node out, 0, weights. Weights exist here. This is getting set by there. So let's say, but how do I specify the weight for node 0? Let's see. Let's come back to that. Oh yeah, let's do this. Set the function, no for the rest of the class. Right, can use X here. Okay, that is fine. And this looks like a C sharp. Okay. So let's try this again. So we have integer of num nodes n, number of inputs, nodes from previous layer, which is 3. Number of outputs, nodes of this layer. Maybe I'm wrong. Maybe it's really it's doing 2 input or sorry, 3 output nodes here and 2 input nodes. Maybe I'm wrong, and it's really number of inputs node from previous layer. And I'm calculating really here, right? So we're saying num nodes in is 2, num nodes out inside of this layer because we want 3 out inside of this layer. So then you say, what does calculate outputs return? I don't like how it's not providing. Okay. So we're saying, let's try this with 2 and 3 instead. So the number of nodes n is coming into the second layer is 2. The number of nodes out of the second layer is going to be 3, right? Because this is also going to be its own layer. Layer 3 with 3 layers coming in and then 2 going out, right? These 2. So inside of here, we have 2 nodes coming in, 3 nodes going out, and biases num nodes out is going to be 3. So you say inputs 2. Weighted inputs equals new double num nodes out, so 3. So there's going to be 3 weighted inputs because this is going to be for the next over here. So there's going to be 3 weighted inputs because that is the number of nodes out set for this layer. So for integer node out equals 0, which is going to be this first node of A, the weighted input for A is going to be based off the bias for 0, which is going to be whatever we set it to. For, and this is basically saying the bias for A, the output node of inside of this layer. Then you say for integer node equals 0, which was this last layer's integer uh, of last layer A, right? As long as this is less than the nodes of A and B, so it's only going to do 0, 1. Weighted input, which is based off of this A right now, plus equal, so we're saying this is 2, plus is equal 7, which is inputs node n 0 from this last one that's already calculated to be say 6. So 6, so 13 plus equal 2, which is 15, times the weights of node n, which we already have over here, and node out, which again we're dealing with the slider. Node out is going to be 0, so it's weights of 0, 0. How this works, I don't really understand. Let's actually go ahead and try to figure that out. Node in, node out. What is this shape of the matrix? Put 0 as weight 0, 0, 0, 1, 1, 0, 1, 1, 2, 0, 2, 1. Index pattern. So what does the inner loop do? For one output node, so for A is the output node, walk down the entire column for that output, multiply each weight by its corresponding input value. So 6, 3, right? Walk down the entire column. So pick output node 0, and then you have input 0, 1, 2, and then weights 0, 0, 1, 0, 2, 0. And I guess the weights are, again, changed as you go through the steps of everything. So weighted input bias 1. Okay. Each output neuron has its own column, the weight matrix. How many outputs are produced? Okay. So weights, biases, uh, bias. What am I doing? How are the weights and bias known prior to being okay? So that's the point of it training, right? It doesn't know exactly what weights or biases to use. It'll just try something and then update these with inside the class for that layer specifically, and then now to keep being able to update, et cetera, et cetera. Okay. So these are within the matrix of weights for each connection to that node out, and then weighted input. So let's say this is for all the weights of this specific 0, 0 weighted inputs of node out, which is A, equals the weighted input. So let's say this is 0. So now we're saying the weighted input for node A for 0, I mean for node 0, which is A, is 15. We do the same thing with B, and we get 20. Let's say we get 14 for C. Now we do the same thing for safe, and we say, okay, this safe output of 0 is going to be layer 3, as we can see, right? I'm gonna get a drawing pad too, so that I can do this without it being so messy. But let's do one more time. So come here. Can I change the brush actually? Marker, brush. That's nice actually. I like that. Okay. So we have now layer 2, layer 3. You have A, B, C, and this is going to safe or poisonous. Okay. Mm, So first and foremost, you start off layer 3, and you're saying num nodes n is going to be 3. So ni is 3. And then num nodes out, I want to output 2 nodes. And o is 2. Okay. Now your weights and biases aren't set yet, but after, programmatically you set this layer, after you do multiple runs and iterations and future reference, yada yada, it will have a certain weight and bias already set. So then you run the constructor. Num nodes in is your three. Num nodes out is your two. Weights and biases. So now you have a matrix for weights set by num nodes in, num nodes out,
the
which is the size. I see. Weights is the size of num nodes in, num nodes out. So it's going to be 3 by 2. So 3 right side, 2 up and down, uh, which will have certain weights to it. And then public double, then you have your function, which is going to have your inputs. And these inputs is going to be the array of the weighted inputs here, which we determined were, I think it was 15. It was like 15, I don't know, 12. 10. So these are your inputs here. And then you start by saying your double of weighted inputs. Weighted inputs is an array of how many nodes outs that you need. Right? So this is going to be an array of two elements because you need safe and poisonous. It's the worst S I've ever seen in my life. So from there we say for each node n, 0, 1, 2, while node n is less than the number of nodes n, which we've already said are 3. So 0, 1, 2 is less than 3. Perform this function. Weighted input, which is here, plus equal, well, really, it's starting off with a bias. Sorry, we're here actually. We're starting off with the weighted input variable being bias of node out, which is we're starting with safe. So whatever the bias for safe is set to be, is what we're starting with. So then we say weighted input, this random variable that we created, is going to be equal to, well, okay, so really we'll call this bi weighted input plus bi, right? This is 0. This weighted input starts 0, but then you say plus the bias of a equals the inputs of node n, which we are counting as 0 right now, so 15 equals 15 plus times the weight of whatever value we're saying is the connection to 0 and safe. So whatever this connection's weight is how we use it, how we utilize it. And then we come back and we say same concept, weighted input for safe, right? Since we're still working on the node out, but we still need to calculate weighted input, right? So then we run this again, and we're saying B now. So input of node n, which is 1 at this point, is going to be 12 because that was the weighted input we got from the last run. And then we multiply it by the weight of connection B to safe, which will get us another number. We'll just say 12 for now. And you see we're plus equaling that. And the same thing for 10. Our connection to 10 would have inputs node n, so it's 10 times the weight of that connection from C to safe, right? So from there, we have weighted inputs of node out. which is safe, all calculated for A, B, C. Every single layer of our convolution layers were found, calculated, summarized into the final result of, say, 37. Right? So now, same concept. We do A and its connection to P, poisonous, right? But let's say C, and we'll call this the size of the fruit, really holds no bearing. So the weight is zero point 0.5, perhaps, while the weight for everything else is 1, right? So this is zero point 0.5. So now C is really 5, which is going to give us 27 and 32. So P equals 32. So because the weight, even though all data may be the same, right? Because there's less weight here, that's how you could change the the 37 anyways, 32. That's how you can change the difference between these. That's the role that weight is playing, which realistically will say, okay, this is 9 instead of 10. We'll say this is 9 just so it's a different situation. But let's say this is uh 16. I'm okay. This might be something that I need to come back later to explain. I understand the concept, but I really want to explain it a bit more cleanly. The fact that because the weight for A might be 2.0, where this is spike length, right? And the weight for fruit size might be, let's just say it's only one, right? The 17 spike length is going to have way more drastic effect to the overall calculation than if the fruit size was 10 instead of 9. Does that make sense? Let's try to let's see here. So if we have A and B, and these connect to C and D, right? And then boom. Okay. If the weight for the connections to C are 2.0, while the weights to connection to D are 1.0, any change to A on a connection to C or B on a connection to C, right? Well, there's a weight for each separate connection, right? So there's going to be a weight specifically for B going to C, for A going to C, etc. So let's say it's 1.0 here. Let's say it's 1.0 here, and we're using zero point 0.0 because they're doubles. So what we could say is, due to gradient descent, we recognize and we find the pattern that A, if spike length, the spike length has a high correlation to if it's safe or not, but it does not have a high correlation to if it's poisonous or not. The same way your forward lean might have a high correlation to it being a receiver, but not necessarily a cornerback. So the weight of forward lean for receivers specifically might be higher. So if you open the matrix and you say uh you have, yeah, let's open up this matrix, and let's say you have receiver, cornerback, and you have forward lean, and you have foot separation. The forward lean aspect to a receiver might hold a weight of 2, while for a cornerback might be 1.5. And the foot separation for a receiver has a lot of weight to it, honestly, because the further away the separation is, the more likely it is. And in a sense, it doesn't really have much to a cornerback. So now you can see the more lean and the more separation, the more likely it is for it to be a receiver due to the weights, where the less likely it is for it to be a cornerback due to the weights. This is how I'm understanding it, of course. As I always say, as we keep going forward, the it may factor out a little bit differently, but so for that same concept, we could say, okay, for a node zero, you could do these calculations, get the new weighted input, which is really just going to be treated as the output for that specific layer.
corresponding weighted input
Right?
to that node's bias value, and then looping over all the incoming values, multiplying each of those by the weight of their connection,
Uh huh.
and adding the result onto the current weighted input.
Uh huh.
For now at least, these weighted inputs are then returned as the output of the layer. Next, we have the actual
As I just said,
weighted inputs are then returned as the output of the layer.
the weighted inputs are returned as the output of that layer.
Next, we have the actual neural network class, which contains an array of these layers.
So then you have your layer. So now let's just keep drawing it out, right? Keep visualizing what's happening exactly. So now you have layer one. One. You have the hidden layer of layer two. Then you have the final output layer, layer three. So now we have a class of neural network, which is an array of these layers, which is how it maintains the weights and biases because we are creating that class of the network and each layer inside of it. So public neural network, we have parameter of integers layer sizes. Layers equals new layer. So you're getting the variable of layers from, and it's an object of class layer uh, created from layer sizes dot length minus one. So ints. So you iterate through all the layers, doing stuff.
So when a
Hold on.
network is created, it needs to be told how
Inputs, run the inputs value through the network to calculate. So then you're utilizing that calculation to determine the outputs and then run the inputs through the network and calculate which output node has highest value. So then you return the highest value. Um, this though will be done only for the final layer in a
how
sense,
many nodes there should be in each
which I don't see where it's being called at exactly, but that's okay. Okay, cool.
To make this out, adding an extra layer doesn't help at all. At least, not on its own. To make this boundary bend, we're going to need to allow the layers to have a non-linear effect on the output. So let's go back to our
Which
design
goes back into activation functions, which is kind of where we left off, and got us here in the first place. Um, so I think this is a good stopping spot. We went way over on time, just really digging into how the layers work, how the inputs and outputs all interact with each other. But that was a lot, and that was really good in my opinion. Let's see. I mean, do we really need notes? We really. This is one of the things. Also, is when you go down this learning path, this learning style of taking everything down to its core and rebuilding it up, you don't really need too many notes. I mean, we understand now a layer, not what we don't need to understand what weights and biases are doing necessarily, because we understand at a core level what it's there for. We would almost feel like something's missing if we tried to explain layers without weights and biases. You see what I'm saying? So I really don't have much to add here, but I will say this will be that. And I hope you guys feel as comfortable with layers and biases, weights, uh, as I do. And we're just gonna keep chugging along, keep going forward. We definitely didn't get through as much of this video as we wanted, but that's okay because that means there was a lot to learn and we learned a lot. So We're gonna keep chugging it along through this video bit by step, until we are finished, and then we'll be able to continue on with our project. So this is good, and yeah, that's all I got for y'all. I hope you have a good rest of y'all day.